Hello everyone, we are going to do second part of section 11.5, which is talking about absolute and conditional convergence. Before we start giving definitions, I want to consider one special series for which our tests are not going to work. So let's look at the next series. The series is going to look like this: cosine of n divided over n squared. N goes from 1 to infinity. I'm going to write down first few terms of this series so you will understand like how it's not going to work. I'm going to round up the values of cosine to two digits after decimal point. There are, of course, much more digits, but I'm going to just to be able to write down quickly the terms of the series. So I calculated actually cosine of 1, cosine of 2, cosine of 3, and cosine of 4, and cosine of 5, and cosine of 6. And I think that was all I calculated. But I want to illustrate something. Well, this is a nice series which has a cosine in numerator and square in denominator. And if I look at the terms of this series, they are not alternating. They do have some pluses and some minuses. So I cannot use alternating series test on it. Also, I cannot use integral series test on it, just because if you look at the expression, I won't be able to calculate the integral. And the function is not going to be decreasing. It's going to oscillate actually, right? I cannot use comparison tests on this because the terms are not positive. I have like bunch of positive terms, bunch of negative terms, and actually they are coming in random order depending like the value of the cosine, right? So what kind of test I can use on this series? I'll need to develop a different kind of test, and this different kind of test is going to be absolute convergence. So let's start with definition now. Definition. A series AM is called convergent absolutely if the series of absolute values so you take the same series but take absolute value of each term is convergent. Uh, well, it's not going to help us to solve the problem. If we just take absolute values and investigate this series, maybe it's going to be convergent absolutely, but how the absolute convergence or this special type of convergence is related to just normal convergence, the convergence of the series, because usually we are interested in finding whether actual series is convergent, not like absolute values or like artificial series is convergent. Theorem. If the series AM is convergent absolutely, then it is convergent. So if the series is convergent absolutely means that if absolute values of the series is convergent, then original series is going to be convergent. So absolute convergence is a strong type of convergence. So actually this theorem is going to help us to deal with this cosine series. Well, maybe let's do it. And then we give one more definition. What is going to happen when the series is not convergent absolutely. But let's first consider this series and see how it's going to behave. Again, you can look at the proof of this theorem. It's a very, very short couple of lines in the book. I don't have time for this, but I'm going to kind of solve the problem and you will see like how everything is working. So I'm investigating this series, a series of cosine of n over n squared, and I do know that this series is partial alternating, not alternating. I'm going to build a series of absolute values. So I will build series absolute value for n. So how it's going to look? Well, I'm just going to take absolute value. That's it. No, there is nothing special in the word absolute. Just absolute values, right? Because n is already positive. I'm just going to get absolute values of cosine of n over n squared and over here to infinity. How absolute values are better than original series? Well, they are better than original series because I have lots of tests which are dealing with positively termed series. For example, I'm going to use comparison test. I will use direct comparison test. Direct comparison test. So I'm going to compare the term of this series. Cosine n over n squared to the series. I'm going to put it in parentheses 1 over n squared. We remember what series is this? This is P series, right? P series with P equals 2 convergent because it's greater than 1. I remember, I'm going to compare. Well, why this comparison is true? This comparison is true because cosine of any number is less or equal than 1 by absolute value because cosine oscillates between -1 and 1 maximum. So if I divide both sides by n squared, it's going to give me a true inequality. So my series is less or equal than convergent series. Then I'm going to make a statement that my series is convergent by, and guys, I don't want to copy it, by direct comparison test. I just did a direct comparison, compared it to a P series with P equals 2, which is convergent. So what is my next step? My next step is to go to the theorem and tell, now, by the theorem, about absolute convergence, my original series, original is cosine without absolute value, is convergent. Usually, guys, all mathematicians know that absolute convergence is stronger than just convergence. So if you say that something is convergent absolutely, you don't even need to mention the theorem. Everyone is going to understand that it's just convergent. Everything what is convergent absolutely is going to be just convergent. Well, very good. We kind of invented a new type of convergence, defined, and then we had a theorem, and you can look up the proof. The proof is not very long, but it's going to consume some time. And we can now use absolute convergence against series with not direct alternation of terms. Because like if terms are positive or all terms are negative, we can apply our test like comparison test, integral test. If terms are alternating, we can use alternating series test. But if terms are randomly changing the sign, we are going to use absolute convergence if we don't really can predict like how the terms are going to change the sign. Now the question is, well, if we do have absolute convergence, is it actually equal to just convergence? Is it like if something is convergent, is it going to be convergent absolutely automatically? And to show this, I'm going to consider example. Example number 2. Let's consider alternating harmonic series. which would alternating harmonic. We know that it's convergent by alternating series test, right? Alternating harmonic is convergent. Let's look how behaves absolute values. If I take absolute values of this series, -1 to the power of n minus 1, in what kind of series I'm going to have? Well, basically absolute value is just going to eliminate the minus, right? Which means that I'm going to get 1 over n from 1 to infinity. And this is just normal harmonic, just harmonic. And we do know that just harmonic is divergent. Well, remember integral test and ln and like going to infinity, divergent. So guys, we do have a series which is convergent, but absolute values are divergent. If you take absolute values, they are divergent. This type of convergence is going to be called conditional convergence. So I'm going to say conditional. And I'm going to give a definition. One more definition here. We have absolute convergence and we have conditional convergence. Series AN is convergent conditionally if it is convergent, but let me move it up, not absolutely. A series of absolute values is divergent. So we call this type of convergence conditionally. Well, you will probably ask me, why do we make this like, okay, this series with cosine was solved. Maybe that's it. I would say that, yeah, for cosine series, absolute convergence is working. But also, guys, interesting idea behind conditional convergence and why we call it a weak convergence is that rearrangements in the sum of series are going to change the sum if something is convergent conditionally. I'm going to kind of put a little star. If you wish, you don't listen to this, you can skip it. Rearrangements. What means rearrangements? Let's consider a series 1 over n squared and from 1 to infinity. And the terms are 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Absolute values of this series is exactly same series. So we know that this series convergent absolutely. Because absolute values is the same series, and we know that the P series equal P equals 2 greater than 1, convergent. Convergent, not just, but convergent absolute. If I rearrange terms in this series, if I put like a first term and then I put a third term, and then I put a fifth term, and then I put a second term, and then I put term number 7, term number 9, and then I put term number 4. I'm kind of pushing odd terms in front. It's going to give me exactly same sum. This is going to be same as the sum of this series. So it's the same sum. So if the series is convergent absolutely, no matter how you rearrange the terms in the series, the sum is not going to change. Now, consider another. Example number 4, right? Maybe 5. Example number 5. If the series is convergent conditionally, I'm going to consider this -1 to the power of n minus 1 over n, alternating harmonic, which is going to be 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5 minus 1 over 6 plus 1 over 7 and so on. So If I rearrange the terms in this sum, I'm going to do same rearrangement. I'm going to put two odd terms first, and then one even term which comes with minus next. And then two odd terms, 1/7, 1/9, minus 1/4. Well, I'm going to show it in class. I'll need a computer to show or graph. So here you will need just to trust me. If you start doing partial sums, here partial sums are not going to be converging to the same number as these partial sums. Just look like what we have. 1 minus 1/2, it's 1/2, plus 1/3 is going to be like, 5/6 probably. And then minus 1/4 is going to be somewhere like a little bit less. If you do this addition first and then subtract this, your number is going to be slightly bigger for partial sums. These partial sums are going to be a little bit bigger. And because of that, they are going to converge to a different number, a little bit bigger number. Actually, guys, the point here is that you actually can converge this sum by making rearrangements to any number. And this is a tricky part in conditionally convergent series. This one, convergent conditionally. Oh, we just looked at it. Absolute values are divergent because they are harmonic, but alternating harmonic is convergent, right? If you rearrange the terms, the sum is going to be a different sum. I'm going to write down S, and a sum of this arrangement is not going to be equal to the sum of this arrangement. And actually, if you look up in the book, it takes a while to show it, but you are going to see that actually it can go to any number. So conditionally convergent series are a little bit tricky. If you move the terms around, they are not going to converge to the same number. You'll probably ask me how this is possible. We know that if we take a sum of numbers and we rearrange the terms in this sum, we must have the same number. This is one of the laws we start learning algebra. Yeah, guys. When you deal with finite sums, where sum has 3 terms, 10 terms, 1 billion terms, that's going to be true. The sum is going to be absolutely same no matter like how you rearrange the terms. But if your sum has infinitely many terms, infinity is like a very, very deep pit from where you can pull anything you like. And infinity is very, very tricky. And that's the reason why we can, by rearrangement, make it to a different number. So typically question about convergence is going to ask whether the series is convergent absolutely or conditionally. I am going to consider one more example of convergence just to make sure that you guys kind of get the idea. One more example, example number 6. And please practice with this. This is a hard stuff to understand, but if you kind of do it step by step, is not like super difficult. Let's consider this series. So I'm going to build absolute values to check absolute convergence. It's alternating, but let's see if it's convergent absolutely. When I do absolute values of this series, I'm going to have just drop -1, right? N over 2n squared plus 1. And I'm going to compare it to a series n over 2n squared. Well, because this plus 1 is making denominator bigger, the number is becoming smaller. And this one is what? 1 over 2 and 1 over n. Oh, sorry. 1 over n. Comparison is not a good comparison. I should do the limit comparison, actually. You see, I got 1 over n. See, I did a comparison, but my series is less than divergent one. This one is divergent. Well, always when you get this, you can do limit test. If you see that your inequality is not giving you the desirable result, you can always do the limit test. Well, a limit test is not going to change the fact that something is convergent or divergent. It's just going to make it more logical because here what we have. My series is less than divergent series. Well, basically it can be another divergent series, which is less than ours. But in this case, it's going to be just like divergent. I'm going to divide my series n, or 2n squared plus 1 over 1 over n. And maybe I'm going to use this one. Usually, the good idea is to use non-simplified version of your comparison series, because this is going to cancel better. Like you see, cancel this, and it's going to give me 2n squared over 2n squared plus 1. Kind of obvious that the limit is equal to 1, then goes to infinity. So you can say that because this one is divergent as harmonic, you can say that it is divergent too. So we have a series which is not convergent absolutely. Let me make a conclusion. Conclusion, not convergent absolutely. Well, maybe it still has a little chance to be convergent conditionally. For conditional convergence, I'll need to check different tests. I'll need to consider the minus, right? Looks like it's alternating series. I'm going to use alternating series test over here. So number 2, limit n over 2n squared plus 1. Remember that when you deal with alternating series, your bn is just everything without minus 1. And kind of obvious if you divide by n over here that the limit is equal to 0, right? We have 1 over here, and here is going to be 2n. Number 1, we'll need to show that it's decreasing. Well, again, look at what we need to do. If we put n plus 1, we need to show that bn plus 1 is less or equal than bn. So n plus 1 squared, and here 2, and plus 1, which is supposed to show that it's less than n 2n squared plus 1. I don't know, guys. Maybe inequality is going to be not too difficult to consider here. I don't really know. I'm going to consider inequality. See how inequality is going to work. So everything here is positive, so I can multiply crisscross. So I'm going to do it n plus 1 multiplied by denominator 2n squared plus 1. It's supposed to be less than n 2n plus 1 squared plus 1. Wow, lots of calculations, but I'm hoping that it's going to result into obvious inequality. So what I have, 2n squared by n, it's 2n cubed, right? Plus 2n plus 1, 2n by 1, 2n squared, plus n by 1, n, and 1 by 1 is 1, supposed to be less. Let's kind of open everything here. We have 2n squared plus 4n plus 2 plus 1. And guys, I'm going to develop this side because I don't want to rewrite the left side. So it's 2n cubed plus 4n squared plus 2 plus 1 is 3. And I'm going to cancel now something which repeats on both sides. Well, 2 cancels, and here we're going to have 2n squared. And 1n cancels, and we have 2n, and this one is going to stay here. Less or equal 2n squared plus 2n. Is it true? Let's remember that n is 1, 2, and so on. So for 1, it's going to be true, right? If you plug in 1 over here, it's going to be 2 plus 2, which is 4, and everything greater than 1 is going to be, of course, greater. But if you want to make it absolutely strict, you can write down that n is greater or equal than 1. Then 2n is greater or equal than 2. N square is greater or equal than 1, just squares this. And then 2n square is greater or equal than 2. So when I add, I'm going to get 2n plus 2n square is greater or equal than 4. And of course, it's greater than just 1. Like, so my inequality is working. Just like this number is actually greater than 4, of course, it's going to be greater than. Okay, so I proved that inequality is working. I checked my second test, and I can say that by alternating series test, the series is convergent. What I have now, well, took me too long to prove. I'm going to make it smaller so I can show you both conclusions because I actually did two tests over here. I tested actual series and I tested absolute values over here, right? And I see that by alternating series this is convergent, but it's not convergent absolutely. I'm going to make a conclusion. My conclusion is the series. You can copy the series if you wish, because there are so many different series. So it may make sense to copy original series. 2n squared plus 1 is convergent conditionally. Okay. Well, that's a conclusion you are making. Okay. So that's all about absolute convergence, and we are finishing section 11.5 at this point. Okay, I'll see you in our next video.